Hello. Today I'd like to talk to you about a concept called effective volume. This is something that I thought up of when I was walking around on campus as a freshman, thinking about passing people on the sidewalk and about whether or not people's paths might collide during the time of their walking. But effective volume is not an original idea, and in fact, I found out that in engineering there's a very similar concept called swept volume. So, we'll start off with that. Swept volume. If you take a cylinder, if you take a piston in a car that's moving back and forth, and it has an oscillation, it's going back and forth inside of the cylinder like that, then it will have a swept volume, which is the volume that is taken up throughout its entire motion. If you take the integral of a circle, which, because pistons are circular, we're going to use a circle, of radius r, and you integrate that circle over this distance L, then you will have the swept volume of your cylinder. Now, this is an important concept in engineering because if you have some kind of speck of whatever inside of your cylinder and it is within the swept volume of your piston, then that's going to cause problems. In engineering, you don't want some object to be within the path of another object that's moving because obviously they're going to collide, they can damage things. Now, this only takes into account the actual total volume of the entire path, but doesn't take into account movement. And that's where effective volume comes in. So, take a system of two objects. One of them will be moving in an oscillatory motion, so back and forth or in a circle. Any motion that's going to return to the same point consistently with a period. Or maybe it's even decaying, but that's for another day. And the other object will be moving into the path of that one. So, object A, let's say for this example it's moving in a circle. Now we have object B over here. Let's say that object A has an initial velocity that's like really fast. And object B has some velocity that's like this. Now, object A is going to take up the effective volume of a donut that's looks like this. Now, A is moving around like this. And if you take B and you put it through, what's going to happen? It's probably going to collide. Here's a conjecture for you. If A is moving sufficiently fast enough relative to B, faster than B, then B will collide with A, no matter where in A's path that it moves, or what time that it moves through that path. Now, I have not proved this, but I do think it's pretty obvious. Let me lay out an example for you that might make more tangible sense. All of us have faced desk fans in our lives. They have a couple of blades on them when they're still. Something that holds them up into the air, and they have a base on them too. Now, this is not the regular state of a fan. They're usually moving because that's when they're useful. So, one thing you might have noticed is that when you look at a fan in real life, they don't exactly look like blades that are sitting there when they're moving. They look more like a semi-translucent disc where these blades are moving and oscillating within there. One thing, too, that I bet that you know is that if you take your finger and you try to stick it into the fan, your finger will get hit by those blades. And if it's a metal one, you might get injured. Now, another thing that you might know is that because the fan is moving so fast, if you take your finger and put it through, it'll be just like that. It'll collide as soon as your finger hits that disc. Your finger will get injured. As soon as you touch it, you're going to feel it, you're going to hear it. And it's all going to happen at the same time as when you see your finger touch that disc. So relative to you, and relative to the speed that your finger is moving, that fan has an effective volume that will be that entire disc plus the width that it is. We can find that by integrating. So now we will begin trying to model a fan. What we're going to do is, instead of modeling 3 blades, we're just going to model 1 blade. And the reason for that is because we don't need to take the integral 3 times. I have 3 blades there, but if you had a 5-blade fan, you also would not want to integrate over all of the blades. However, there are cases in which you would want to, and then you would just, it would be fine. It would just, you'd have to subtract out the areas that are taken up twice or multiple times. But if you had blades that were offset from each other a little bit, and they were taking up different volumes as they were moving through, then you would have to do that. But for this example, we're going to model it just using 1. We're going to have some kind of axis here, y and x, and we're just going to say that we have our blade. At time 1, it will be there. At time 2, it will be there. At time 3, it might be there. Time 4, it will be there. And we can see that as a period, angle-wise, of 2 pi, or it has an angular distance of 2 pi in this oscillation. Now we're going to take an object, and at time 1, it will be here. At time 2, it will be here. Time 3, it will be here. And time 4, it will be here. Consider this. In a moment, we're going to move on, and I'm going to show you some Maple code that's demonstrating this. And I want you to think, is this ball going to collide with the fan, or will it not? All right. So instead of modeling our blade as a whole blade, for right now, we're just going to model the point that's the tip of our blade. And we're going to model it using a helix. This is because normally it's a circle, but we're moving in the z-axis as well, or really the time axis as well. So if you look here, we have x and y for this parameterization. It's equal to cosine and sine, which is a circle of radius 1. And then now we're going to move it through our z-axis, which will be our time axis, here like this. And then we're going to move it through 1 oscillation's worth. Now we have our ball as well that starts to the right of our blade by about 1, and it's going to move to the left. Because you remember that the ball was like here, and then it moved over. And then the ball was at a stable height the whole time. So we have that, and it's moving through time at the same speed as our blades, even though it might not have the same physical speed. So here we go. Here we can look at that now. Okay, so the path of the tip of the blade is in blue, and the path of our ball is in red. One thing I want you all to recognize is the fact that this is a space-time diagram, except our space-time, or space, is only 2-dimensional, and we have a time axis here. And if we move this so that we are just looking at the x-y axes, you can see that our axes are kind of off, aren't they? But you can see that our blades are going to be moving in a circle like so, but they're really a helix because of the fact that, that we're going to be moving through time. And then you can see that our ball moves through on a straight line, and it moves through the path of where the blades are going. But then if we look in the time dimension, we can see that they do not collide. And so we can assume that the time scaling for our object moving through the blades is probably not sufficient for the blades to have an effective volume of a disk for that object.
Now we're going to model it as more like a strake so that we can actually exactly model having the area of the fan blades themselves. And we can see that the blade, it's taking up this whole radius right here, and it's creating a circle, and that's like the circle that is swept out by these blades. But we can see that if we look in this space-time diagram, this object is still never going to collide with our blade. And it moves off and it leaves the whole entire space that our blade is taking up. And it starts outside of that space as well. And it keeps on going afterward. And it does not collide. So how might we find a time scaling in which they do collide? Well, we can leave our parameterization of the strake the same. Just have it be just the way it is, and we will only adjust the object. Now, I fiddled around with this a little bit myself, but if you look right here, this is specifically the speed. This is the parameterization of our object moving through space. And what I decided to do is I had it start just outside of our circle, so just outside of a radius of 1, and then it moves to the left at a slower speed than our strake is moving. And that's because the time is divided by a much larger amount. And then it stays at a steady y, but it still moves through our time axis the same amount. It's only moving in the x-axis slower than it was before. Now let's look. Oh, wait, another thing. I also changed the time of our entire model so that we could look at a larger amount of oscillations of our fan. So now we're looking at 8 oscillations, whereas before we were only looking at 4. So now we can see here that, as you guys can guess, this fan does have an effective volume relative to that object. So it has 8 oscillations here, and it's taking up, and this is the space-time diagram of those blades as I'm modeling it here. And we can see that right here at this point, the ball, our object, pretty much intersects with the fan exactly when it hits the radius of our oscillation. You can see that point right there where it hits, right? Where it touches the radius of our oscillation. And you can see that it actually intersects just a little bit inside of that. So if we had a little bit of a faster time scaling with a little bit different, it would be even more of a relative difference, and this fan would be taking up this volume even more effectively compared to that object. But overall, you can see that this object is intersecting with the fan blades, and it will intersect instantly, relatively, no matter where it hits on that oscillation.
So, in conclusion, effective volume involves a couple of different concepts, but it's not too complicated to understand. First off, it's based on movement of an object within a specific volume. And if the motion of that object has a time scaling that is vastly different than another object, then relative to that object, it will have an effective volume of the volume that it is moving in. And that volume could also be called the swept volume, as referencing engineering. Now, if you want to solve a problem to find what time scaling will lead to intersections and what time scaling will not, you can look at space-time diagrams of the motions, and you can look at you must use the 3D parameterizations of these objects within these space-time diagrams in order to fully understand how the volumes of the motions will intersect. Thanks for listening, and I hope that this was interesting, and I hope that it intersected with the concepts of differential geometry enough to be a suitable video for a final project. Thank you.